Good day, everybody. My name is Victor Solomon, and I'll be giving a presentation on our paper titled EdgeAttNet towards Barb-Aware Filament Segmentation. This presentation would include 6 parts. First part, talk about the background and motivation. Then we'll talk about the data and preprocessing. Then we'll go ahead to talk about the methodology and then the evaluation metrics that's been employed. We'll also discuss the experiments and results of the study, and finally give conclusions. I'll begin by talking about the background and motivation of this research. Filaments are elongated dark structures of cool plasma formed along polarity inversion lines in the chromosphere. They have similar intensities with sunspots when viewed in H-alpha observations, as can be seen in the image on the right. You can tell by looking at the sunspots and the filament on the H-alpha image that they have similar intensities. Filaments are key precursors to coronal mass ejections, given that their chirality or handedness influences the magnetic configuration of CMEs. Now, why do we focus on Barb-Aware segmentation in our research? This is because the barbs of a filament can tell the chirality of the filament, and also because accurate segmentation of filaments capturing the detail in the barbs is essential to improve chirality identification, as can be seen in the images on the right. By the barbs of the filament, we're able to tell that it's a left-bearing barb or it's a right-bearing barb. I'll talk about the limitations of current research. Current filament segmentation models do not weigh in the importance of capturing the barbs of filaments during segmentation, as they majorly consider just the IOU and the region covered. As can be seen in the image on the right, we have a ground truth filament GT that shows the barbs of the filament, and then we have 2 predictions that's been made by some models, P1 and P2. Current segmentation models for filaments will prioritize P2 over P1 just because it captures more region of interest than P1. But in the real sense of it, for conducting downstream tasks like chirality detection, P1 is actually a better prediction than P2. The second challenge from current research is that they do not adequately handle noise in H-alpha observations before building or training their models. As a result, we have 3 research objectives. The first is to build a robust H-alpha processing pipeline. The second is to build accurate pixel-wise Barb-Aware segmentation models, and then to evaluate the models using Barb-Aware evaluation strategies. I'll talk about the data and preprocessing we have done. We used H-alpha image data from GONG, which GONG has 6 observatories. Each site in GONG captures data at a 6-minute cadence, giving us a global cadence of 1 minute capturing of H-alpha images. The image on the left shows a H-alpha image from GONG, and the image on the right shows the 6 different observatories that constitute GONG. We also use annotation data, particularly from MagPhilo. MagPhilo contains 10,245 annotated filaments, 1,593 H-alpha observations from GONG from the years 2011 to 2022. The annotation includes polygon segmentation, spine, minimum bounding rectangle, the chirality of the filament. 958 observations are unique, 548 are annotated once, 185 twice, 225 observations are annotated 3 times. This is the reason why we have chosen MagPhilo as an annotation dataset because of its robustness in annotation. As can be seen in the image on the right, a filament is shown on the left, and 2 annotations from 2 annotators are shown, the center and the right. A polygon in this dataset is a polygon segmentation is a list of endpoints that is enclosed. I'll talk about the data preprocessing pipeline we have developed. It takes in raw input H-alpha observation and passes it through a number of steps in the pipeline, then outputs a preprocessed H-alpha observation. The first step in our pipeline, we normalize the pixels between a 0 to 1 range. We use a half cycle transform for disk maxing to locate the center of the disk. We also do radial flattening to correct limb darkening. And we apply Gaussian smoothing kernel, 3x3 kernel, with a variance of 0.7 to reduce high frequency fibril noise. We then apply contrast limited adaptive histogram equalization for local contrast enhancement of filament, and then set all of these pixels to 0. Next, I'll talk about the methodologies. We have used 4 different models, 3 of which are baselines, and then our proposed model, EdgeAttNet. The first is the UNet model. The second is the UNet, incorporating a multi-head self-attention with positional encodings. The third model is the UNet, incorporating a multi-head self-attention with no positional encodings, and then our proposed model, EdgeAttNet. The UNet is a very popular segmentation architecture, and some of its advantages is that it has fast convergence, it reduces overfitting using spatial downsampling, it learns spatial information using skip connections between the downsampling and the upsampling layers. The disadvantage of the UNet is that it fails to recover global dependencies as it is more localized. Now I'll talk about our proposed model, EdgeAttNet. Our EdgeAttNet model is the UNet that's been incorporated with some novel components. The components we have integrated into the UNet to create our model is 1, the edge prior model, and 2, the edge-guided multi-head self-attention layers. I'll talk about the architecture of our proposed model. It includes an encoder, a bottleneck, and a decoder. The encoder has 4 hierarchical stages with double convolutional blocks and max pooling layers to reduce spatial resolution and a number of future channels. It also uses a bottleneck that has double convolutional blocks with 2 edge-guided multi-head self-attention modules. We have done this to promote boundary-aware global context modeling. And then in a decoder, it upsamples with all transpose convolutions and also uses skip connections and future fusion. Now I'll discuss the edge prior extraction and integration with the edge-guided multi-head self-attention. It includes a 3x3 convolution followed by sigmoid activation, and then it outputs an edge map E. A bilinear interpolation of E is done to match the bottleneck resolution, and then a 1x1 convolution is applied to match the channel dimension of the H alpha image. The edge map E is added to the query and key embeddings in the attention mechanism to guide future processing. Now I'll talk about the edge-guided multi-head self-attention modules. We use the standard multi-head self-attention augmented with the learned edge map. This enhances boundary sensitivity and captures better global context. The self-attention completion is done using these equations. The Q, the K, and the V matrices, the query, the key, and the value matrices are computed using these equations. And then a softmax is applied to it. And then a dot product is computed between the result and the value matrices. The number of attentions heads is set to 4, each having a length of 128. Next, I'll discuss the bottleneck integration. Features from the last encoder layer is processed using a double convolution. And then it is followed by 2 edge-guided multi-head self-attention modules. And then the final output is passed to the decoder for upsampling. This table shows the architectural overview of our models. It includes the architecture type, the backbone, depth, the decoder type, and tells us whether protein weights are used. It also tells the type of attention mechanism that has been used. As can be seen, the number of parameters for our proposed model, EdgeAttNet, is way less as compared to the other baselines. Next, I will discuss the evaluation metrics we have used. We use two different evaluation metrics, the IOU pairwise and the IOU multi-scale. IOU pairwise shows the predicted region over the ground truth, but it fails to capture the Barb fidelity during segmentation. As a result, we have also used the IOU multi-scale that gives predictions at different resolutions. This is better at capturing predictions while considering the Barb during segmentation. Next, I'll talk about the experiments and the results. We use 1,593 H-alpha observations from the Gong datasets, but after filtering, which is done by removing H-alpha observations with no filaments, we have 1,494 H-alpha observations. We split our data into the training, validation, and test sets, and then we use this training setup of 50 epochs, the Adam optimizer, and no pre-trained weights for all our models to train the models. Now I'll discuss the result on the test split. This table shows the results we've gotten from our model. As can be seen, our model EdgeAttNet outperforms the baselines by having a mean IOU pairwise of 0.6451 and a mean IOU multi-scale of 0.7032. This tells us that our model captures more region of interest while also preserving Barb fidelity as compared to the baselines. And this is a comparative analysis of the models. As can be seen, our model EdgeAttNet captures the Barb diligently as compared to the baselines. It also shows that it has more or less false positives as compared to the baselines. Now I'll give conclusions of our study. The key contributions of this study include a robust H-alpha preprocessing pipeline. We also developed EdgeAttNet, a novel U-Net-based segmentation model for detecting filaments. And we also proposed edge-guided multi-head self-attention models that enhances the model sensitivity to fine-scale features, which are filament barbs. Also, for computational efficiency, our model EdgeAttNet uses 22 million parameters, which is way fewer as compared to the baselines, which use between 35 million parameters to 35.3 million parameters. And we can categorically state that the advantages of this study using edge priors replace explicit positional encodings and simplifies the architecture. It also shows that we got robust performance in detecting the filament barbs and makes it ideal for chirality classification. Thank you so much for your time. To access the project code base, you can scan this QR code or visit the link here. Thank you.